Now we are moved to the degradation categories in brief. Degradation categories are reviewed here in the context of below figure, already we discussed in the last video, which summarize small scale fading mechanism, degradation categories, and their effects. When viewed in the time domain, a channel is said to be exhibit frequency selective if T suffix m is less than Ts, that is, delay time is greater than the symbol time. The condition occur when the received multipath component of a symbol extend beyond the symbol time duration, thus causes channel induced inter-symbol interference, can be called ISI. Viewed in the time domain, a channel is said to be exhibit frequency non-selective or flat fading if Tm less than Ts. In this case, all the received multipath components of a symbol arrival with the symbol time duration. Hence, the components are not to be resolvable. Here, there is no channel induced ISA distortion since signal time spreading doesn't result significantly overlap among the neighboring received signals. There is still performance degradation since the mitigation degradation effects of fading channels unresolvable phasor components can be added up destructively to the yield substantial reduction in the signal to noise ratio. Already we discussed in the previous video, there is a two types of a mechanisms, time spreading mechanism due to the multipath and time variant mechanism due to the motion. In time domain spreading mechanism due to the multipath, frequency selective fading, flat fading, and similarly time variant mechanism due to the motion, fast fading and slow fading, or in the time domain approach. And second one is in the Doppler shift approach. In the frequency domain approach also, frequency selective fading, flat fading. In the time domain approach, fast fading and slow fading. So each fading is create some disturbances and each fading have its own conditions depend upon the delay spread, symbol time, channel fading rate, multipath delay, and channel coherence bandwidth, channel coherence time, symbol time, and etc. By considering less than or greater than conditions, the fading can be finalized either maybe a frequency selective fading or flat fading or slow fading or some another type of a fadings. When view the frequency domain, a channel referred to a frequency selective if f naught less than 1 by tf is approximately equal to w, where the symbol rate is 1 by ts is normally taken to be equal to the signal bandwidth w. Flat fading degradation occurs when f naught less than w. Here, all the signal spectral components will be affected by the similar manner, for example, fading or non-fading. To avoid the inter-symbol interference caused by the frequency selective fading, the channel must be exhibit flat fading by ensuring that the coherent bandwidth exceed the signaling rate. When viewed in the time domain, a channel is referred to as fast fading whenever T0 is less than Ts, where T0 is the channel coherence time and Ts is the symboling time. Fast fading describes the conditions in which the time duration that the channel behaves in correlated manner in a short compared to the time duration of a symbol. Therefore, it can be expected that the fading character of a channel will change the several times during the time that a symbol is propagating. This leads a distortion of the baseband pulse shape because received pulse components are not all highly correlated throughout the time. They are varying, they are uncorrelated. Hence, fast fading can be causes the baseband pulse to be distortion and resulting in a loss of SNR that often else is irreducible error rate, such as distortion pulse typically causes a synchronization problem as a failure in the phase lock loop receiver as we discussed in the previous video. View in the time domain, a channel generally referred to be a introduces slow fading rate if T0 is greater than Ts. Here the time duration that the channel behaves is in correlated manner is long as compared with the symbol time. Thus, one can expect the channel state is remain virtually unchanged during the time that a symbol is transmitted. Whenever the Doppler shift domain, a channel referred as a fast fading, if the signaling rate 1 by Ts or signal bandwidth W is less than the fading rate or FD. Conventionally, a channel is referred to as slow fading if the signaling rate greater than the fading rate. In order to avoid signal distortion caused by the fast fading, the channel must be a exhibit slow fading by ensuring that a signaling rate exceed the channel fading rate. These are the different types of conditions we are observed in the degradation. Now we move to the second concept, signal time spreading viewed in frequency domain. That means viewed in a frequency domain. A complete analog characterization of a signal dispersion can be specified in the frequency domain. It is expressed in the above figure. Modulus R delta F is designated a spatial frequency correlated function. Can be seen, it is a Fourier transform of SF tau. The function R delta of F represents the correlation between the channel response to signals as a function to the frequency difference between the two signals. It can be throughout of channel frequency transfer function. Therefore, the spreading manifestation can be viewed as if it were result the filtering process. Knowledge of R delta F helps the answer the question. What is the correlation between the received signal that are spread in frequency? That is delta F is equal to F2 minus F1 as a question mark. The function of R delta F can be measured by transmitting a pair of sinusoidal signals separated in a frequency by delta F cross correlating the complex spectra of two separately received signals and repeating the process in many times with a ever larger separation of delta F. Therefore, the measurement of a R delta F can be made with a sinusoidal that is sept in frequency across the band of interest as a wide band. The coherent bandwidth F0 is a statistical measurement of a range of frequency over where the signal passes all spectral components with approximately equal gain and linear phase. There is no changing of gain and with the same linear value. Thus, the coherence bandwidth represents a frequency range over a with signal frequency components have a strong potential of amplitude correlation. That is, spectral components in the range of affected by channel in a similar manner. For example, exhibit fading or no fading. Note that F0 and Tm are reciprocally related with a multiplicative constant. For an approximation, we can say that F0 is approximately equal to 1 by Tm. In the signal time spreading in frequency domain, the maximum exceed delay Tm is not necessarily the best indicator to how many give systems will perform when the signal propagates in a channel, because different channel with the same value of Tm can exhibit very difficulty signal intensity propagation over a delay span. A more useful parameter in the delay spread, more often characterization in terms of its root mean square value called as a RMS delay spread, as sigma of t is equal to square root of t square minus t bar square whole square, where tau square is the mean exceed delay and tau bar square is the mean square delay. Where tau square is the second movement and tau t is the square root of the second central movement of S of tau. The universal relationship between coherence bandwidth and the delay spread that would be useful in all applications does not exist. However, using Fourier transform technique, an approximation can be derived from the actual signal depression measurement in a various channels. Several approximation relations have been developed already. In coherence bandwidth is defined as the frequency interval over with a channel complexity frequency transfer function has a correlating at least 0.9 value. The coherent bandwidth is approximately f0 is equal to 1 by 50 tau t. For this case, a mobile radio, an array of randomly uniform spread sector with all equation magnitude reflections coefficients but independent, randomly occurring reflections phase angles, is generally accepted as a useful model for urban propagation environment. This model to be referred as a dense scatter channel modeling, which is useful. Such a model coherent bandwidth as similar to the defined for a bandwidth interval or a channel complex frequency transfer function at least 0.5 to be f0 is equal to 0.276 by delta t. Study involved ionosphere effect on the employing following equation f0 is equal to 1 by 2 pi delta t. As more popular approximation of f0 corresponding to the bandwidth interval having the correlation at least 0.5, that is f0 is equal to 1 by pi sigma t. The delay spread and the coherence bandwidths are related to the channel multipath characteristics difference for the different propagation paths. It is most important to note neither of the parameters of equations depends on the signaling speed. A system signaling speed only influences its transmission bandwidth W. Now we are moving to next category, degradation category due to the signal time spreading viewed in frequency domain. Already we complete the time domain. Now we are moving to the next part, frequency domain. A channel referred as the frequency selective if f0 is equal to W. Already we discussed in the above slide. Where the symbol rate 1 by Ts is normally taken to be equal to be signaling rate or signal bandwidth W. In practice, many differs of 1 by Ts due to the system filtering or data modulation type. Example, quadrature phase shift key, M-array shifting key, spectrum, etc. Frequency fading distortion occurs when the signaling spectral components are not all affected equally by the channel. Some of the channel's signal spectral components falling outside the coherence bandwidth will be affected differently. Compared with those components content with this coherence bandwidth, the below figure contains 3 examples. Each one examine the spectral density versus frequency of transmitted signal having bandwidth W. Superimposed on the figures is the frequency transfer function of frequency selective channels, shows that variation spectral components of transmitted signal is affected differently. Frequency non-selective fading degradation occurs when f0 is greater than W. That means frequency selective is dependent upon f0 is less than W. Frequency non-selective is dependent on f0 greater than W. There is a relationship between the f0 and bandwidth W. Hence, all the signal spectral components will be affected by the channel in a similar manner, fading or non-fading. Already we discussed in the previous slide. However, superimposed on the plot is a frequency transfer function of flat fading. The below figure explains that all the spectral components of transmitted signal will be affected approximately in the same way. Why? Because it is non-selective fading. But performance degradation can still expected due to the loss of SNR whenever the signal is fading. In order to avoid the channel interference distortion, a requirement exhibit the flat fading occurs provided f0 must be greater than W, that is approximately equal to 1 by Ts. Hence, the channel coherence bandwidth f0 sets upper limit on the transmission rate that can be used without incorporation of equalizer and receiver, equalizing in the receiver. For the flat fading case, whereas f0 greater than W, indicating a mobile radio changes its position, there will be a time when the received signal experiences frequency selective distortion even through f0 greater than W. Whereas the null transmitted signal spectral density is occurred, the baseband pulse can be especially multiplied by the depreventions of low frequency components. One consequence of such a loss is in the absence of a reliable pulse peak of which to be established timing synchronization or from the with the sample carrier phase carried by the pulse. Thus, even though channel categories is the flat fading, it can still manifest frequency selective fading on occasion. It is fair to say a mobile radio classified all exhibit flat fading degradations cannot exhibit flat fading in all the time. As F naught is becomes much more than W, less time will be spent exhibit the type of condition. By comparison, it should be clear fading is independent of the position of signal band and the frequency selective occurs all time. Fading occurs all time and not just occasionally. Here there is a three representation of a signals. In the first one, typical frequency selective fading F naught less than W. Typical flat fading case F naught greater than W. Third one, null of the channel frequency transfer functions occur at a signal band center F naught greater than W. In all these cases, the channel frequency transfer function is observed with respect to spectral density versus frequency. Now, the signal dispersion manifestation of a fading channels is analog to the signal spreading the characterization of electronic figure. The below figure depicts a wideband narrow impulse pulses and the effect of a single signal both in time and frequency domain. The filter resembles of a flat fading channel yielding an output that is relatively free of distortion. The below figure shows a narrow band filter. The output signal suffer much distortion as shown in the both time and frequency. Here the process resembles a frequency selective channel. In the figure number A, flat fading channel characteristics. In the figure number B, frequency fading channel characteristics. In the above part is related to the time domain and the below part is related to the frequency domain. Let us consider S of t as the input signal and R of t is the output signal and H of t comma tau as a transfer function. Now see the variations of S of t and R of t. S of t with a time period of a 0 to Ts, but in R of t there is a spreading of a time Ts plus tau, there is some time delay, but in the frequency Fc is the center frequency and we also maintain the same center frequency of Fc at the output. Similar to the frequency selective fading characteristics, S of t has an input with a time period of 0 to Ts, but observe the output R of t with a time delay version of Ts plus tau. And observe the frequency domain of center frequency Fc and same centering frequency Fc in RF. In both two cases, we are maintaining the centering frequency is equal to constant in frequency domain approach. Now coming to the part number 3, time variations of a channel caused by the motion. Signal dispersion and coherence bandwidth characterize the channel's time spreading properties in a local area. However, they don't offer information about the time varying nature of the channel caused by the relative motion between the transmitter and receiver or by movement of the object within the channel. For a mobile radio applications, the channel is a time variant because motion between the transmitter and receiver results in propagation path changes. For a transmitted continuous wave signal, such a changes causes variations in signal amplitude and phase at the receiver. If all scattered make up the channel or stationary. Whenever motion ceases, the amplitude and phase of the receiver remains constant. Receiver signal remains constant. That is, the channel appears to be time invariant. Whenever motion begins again, the channel appears the time variant. Since the channel characteristics depends on the position of the transmitter and receiver. Time variations, in this case, equivalent to the spectral variance. The mathematical concept of a duality can be defined as follows. The process of dual of each other, if they are mathematically relationship, are the same even though they are not described in terms of difficulty parameters, different parameters. Here, in the above figure, we can identify functions that exhibit a similar behavior across the domains. For the purpose of understanding the fading channel model, it is useful to refer such a functions as a duals. For example, the phenomena of signal dispersion can be characterized in the frequency domain by R of delta of f, is shown in the above figure. It yields knowledge about the range of frequency or a two spectral components of the received signal have a strong potential for amplitude and phase correlation. Fading capacity is characterized by in the time domain R delta of t is shown in the above figure. It yields the knowledge about the span of a time over which two received signals are strongly potentially for the amplitude and phase correlation. These two correlation functions R delta of f and R delta of t can be labeled as a dual in the sense R delta of f is the frequency domain, R delta of t in the time domain. There is also noted that the duality between the blocks in between 10 and 13 figure in the above shown in the above figure, dual relationship in the time spreading mechanism in the frequency domain and time variant mechanism in the time domain. Now, new concept, degradation categories due to the time variance viewed in a time domain. Now, the time nature of a fading rapidity mechanism of a channel can be viewed in two times degradation categories listed in above figure, fast fading and slow fading. The term of fast fading is used to describe the channel in which T0 less than Ts, where T0 is the channel coherence time and Ts is the time duration of time for transmission symbols, which was discussed already in the previous slide. Fast fading describes a condition where the time duration in which the channel behaves in correlated manner is short compared with the time duration of a symbol. Therefore, it can be expected that fading character of the channel will changes several times during the time span of symbol. Leads to described as a channel induces ISI. Here, distortion takes place because of received signal components are not highly correlated throughout time. Hence, fast fading can causes the baseband to be destroyed, often resulting in an irreducible error rate. Such distortions pulses can be synchronized problem. In addition to difficulty of inadequately designing a matched filter. That a channel is generally referred as to a introducing slow fading if T0 greater than Ts, if the time duration in which the channel behaves is a correlated manner is long compared with the time duration of transmitted symbol. Thus, one can expect the channel state is virtually remains unchanged during the time in which a symbol is transmitted. The propagation will likely not suffer from the pulse distortions described earlier. The primary degradation is slow fading channel with flat fading is loss in signal to noise ratio. Now, next concept, time variation viewed in Doppler shift domain. As completely analog characterization of a time variant nature of the channel can be represented in the Doppler shift in frequency domain. For the case of dense scatter model, a vertical receiver antenna with a constant azimuthal gain and a uniform distribution of a signal arriving at all arrival angle throughout the range of 0 to 2 pi. An unmodulated continuous wave signal and the signal spectrum of an antenna terminals is approximately S of V is equal to 1 whole divided by pi fd into square root of 1 minus V minus Fy Fd whole square. The equality holds the frequency shift of a V and that a range of plus or minus Fd about the carrier frequency Fc and would be 0 outside of the range. The shape of the RF Doppler spectrum described in equation above is classically bowl shaped as shown in the figure above. Note that the spectral shape is resultant of the dense scatter channel model. The sharpness and steepness of the boundary of the Doppler spectrum are due to the sharp upper limit on the Doppler shift produced by the vehicular antenna traveling among the stationary scatters of dense scatters model. The largest magnitude of S of V occur when the scatter is directly ahead of moving antenna platform or directly behind it. In this case, the magnitude of the frequency shift given by Fd is equal to V by lambda, where Fd is equal to V by lambda, where V is the relative velocity and lambda is called as a signal wavelength. When the transmitter and receiver move towards each other, Fd is positive, that is the Doppler frequency. When move away from each other, Fd becomes negative, that is minus Fd. For scatter directly broadside the moving platform, the magnitude of the frequency shift is 0. The fact of Doppler components arriving exactly 0 to 180 degrees have an infinite power spectral densities is not a problem. Since the angle of arrival continuously distributed, the probability of components arriving at exactly these angles is equal to 0. S of V is the Fourier transform of R of delta of t. It is known as Fourier transform of autocorrelation function of time series equal to the magnitude squared of the Fourier transform of original time series. Once again I repeat, it is known as Fourier transform of autocorrelation function of a time series equal to the magnitude square of the Fourier transform of original time series. Therefore, measurement can be made simply transmitting a sinusoid narrowband signal and using Fourier analysis to generate the power spectrum of a received amplitude. The Doppler power spectrum of the signal yields knowledge about the spectral spreading of a transmitted sinusoid. In the Doppler shift, the indicating of S of V regulated as a dual of the multipath intensity profile S of tau. Since later yields knowledge about the time spreading of transmitted impulse in the time domain, in the time delay domain. This is also noted in figure above as the duality blocks 7, 16 and others. The duality between the time spreading mechanism is the time delay domain and the time variant mechanism in the time shifting domain. The knowledge of S of V makes possible to estimate how the particular S of how much of spectral broadcasting imposed on the signal as a function of a rate of change in the signal state. The width of the Doppler power spectral Fd is referred to the literature several different names: Doppler spread, spreading rate, fading bandwidth or spectral broadening. The equations which we are using in the above describe that Doppler frequency shift. In typical multipath environment, the received signals travels over a several reflected paths, each with a different distance and a different angle of arrival. The Doppler shift of each arriving path is generally different from that other paths. The effect on the received signal manifests itself as a Doppler spreading of a transmitted signal rather than the shift. Note that Doppler spread Fd and coherent time T0 are reciprocally related, resulting an approximation relationship between the two parameters is given T0 is equal to 1 by Fd. Hence, the Doppler spread Ft is graded as a typical fading rate on the channel. Earlier, T0 is described as the expected time duration over which the channel responds to a sinusoidal essential invariant. When T naught is defined more precisely as time duration over which the channel response sinusoidal is, a correlation between them at least 0.5 already we discussed. Relationship between the T naught and FD is approximately T naught is equal to 9 by 16 pi FD. The popular rule thumb to be defined T naught as a geometric mean of equations, and T naught is equal to square root of 9 by 16 pi FD square, that is equal to 0.423 FD. For this case of 900 MHz mobile radio, the typical effect of relay fading on the signal's envelope amplitude versus time. The figures are indicating the distance traveled by the mobile in a time interval corresponding to the adjacent nulls in order to of wavelength lambda by 2. The time required to the travel of distance lambda by 2 when the traveling constant v is equal to T naught lambda by 2 divided by v, that is equal to 0.5 divided by vd fd. Thus, when a time interval between the fades is approximately lambda by 2, the resultant expression of T naught is quite choice by considering some of the mean parameters like velocity is equal to 120 km per hour and the carrier frequency is approximately equal to 900. In a straightforward to determine the channel coherence time approximately equal to 5 milliseconds and the Doppler spread is approximately equal to 100 Hz. Therefore, if this example represents channel over which digitalized speech signal are transmitted to a typical rate of 10 to the power of 4 symbols per second, the fading rate is to be considered less than the symbol rate. Under this condition, the channel would manifest through fading effect. Note that it is a abscissa were labeled in units of wavelength instead of time. The plotted fading characteristics would like to the same for any radio frequency or any antenna speed. Now let us consider analogy for the spectral broadening in the fading channels. In the left hand side, we consider sinusoidal signal, keying signal, digital signal, faster keying and digital signal in time domain. In the right hand side, we consider all these effects in frequency domain. In the figure, A is the ideal rectangle on-off switching duration, not A, is B. Signal A is indicating a sinusoidal with a range of a minus infinity to plus infinite or maybe a cos signal minus infinity to plus infinite, and figure B indicating a rectangular on-off switching function. The frequency description of these switching functions in a sync ft. The figure number C results the multiplication else a tone of cos 2 pi fct, that the time duration is limited. The resultant spectrum obtaining by convolving of spectrum impulse as a part with a sync ft function as a part, else a broadening spectrum in the part number C. It is further seen that if the signaling occurred at a faster characterized by the signal shorter duration is in figure number D, the resultant signal spectrum as a resultant E exhibits greater spectral broadening. The changing state of fading channels is somewhat analogous to the on-off keying digital signals. The channels behaves like as a switching, turning the signals on and off. The greater rapidity of the channel in the channel state, greater spectral broadening expected by the signal propagation over such a channel. The analogy is not exact because on and off switching of the signals may result in the phase discontinuous, while the typical multipath scattered environment induces phase continuous effects. In the next chapter, degradation of a category is due to the time variation viewed in a Doppler shift domain. A channel is said to be a fast fading if the symbol rate 1 by Ts is approximately equal to the signaling rate W is less than the fading rate 1 by T naught. That is, fast fading is characterized by W less than Fd or Ts greater than T naught. The channel referred to a slow fading, the signaling rate is greater than the fading rate. Thus, in order to avoid the signal distortion caused by the fast fading, the channel must be exhibit slow fading characteristics by ensuring that signaling rate exceed by the channel fading rate, that is W greater than FD or TS less than T0. The coherent bandwidth F0 set an upper limit of the signaling rate that can be used without suffering the frequency selective distortion. Similarly, the equations that shows due to the Doppler spreading, the channel fading rate FD sets a lower limit for the signaling rate that can be used without suffering the fast fading distortion. For HF communication systems, while tele type of Morse-coded messages were transmitted at low data rates, the channel often exhibits fast fading characteristics. However, most present day terrestrial of mobile radio channels can be generally characterized as a slow fading. A better way to state requirement for the mitigation, the effect of fast fading would be the desired W greater than FD. If the condition is not satisfied, the random frequency modulated due to the variation of Doppler shift will degrade the system performance significantly. The Doppler effect yields an irreducible error rate that can be over a simple increasing of E by N0. The irreducible error rate is more prone for any transmission scheme that involves modulated carrier phase. A single specular Doppler path without scattered, the register instantaneous frequency shift classified and calculated as Fd is equal to V by lambda. However, a combination of a specular and multipath components yields rather than complex of time-dependent instantaneous frequency, which can cause frequency swings much larger than plus or minus V by lambda. When the information is recovered by an instantaneous frequency detector, it can be happened. Owing to vehicle motion, the time of T1, specular phase has rotated through an angle of theta, while net phasor has rotated with a theta with an angle of phi, which is about the 4 times greater than theta. The rate of change of phase at a time near to the particular phase about 4 times that a specular Doppler alone. Therefore, the instantaneous frequency of shift d phi by d theta would be 4 times that a specular frequency shift. The peaking of instantaneous frequency shifts at a time near to the deep phase at it can be take phenomena of FM, clicks or spikes. The above figures bit error rate versus CB by N0 will be supporting for DQPSK signaling at F0 at 850 MHz. It should be clear that at high speed, the performance curve bottom and error rate equivalent to the may unacceptable high. Ideally, the coherent demodulation that lock on to and track the information signals should be suppress the effect of FM noise and thus cancel the impact and Doppler shift. However, a large values of FD carrier recovery of difficulty to implement because very wideband phase locked loops needs to be designed. For voice grade applications, bit error rate is approximately 10 to the power of minus 3 to 10 to the power of minus 4. A large of Doppler shift is considerably needed is 0.01 into W. Therefore, avoiding of fast fading distortion and Doppler introduced by the irreducible error rate. The signaling rate should be exceed by the fading rate by a factor of 100 to 200. That exact the factor depends on the signal modulation, receiver design and requirement error rate. The process is explained in this Figure, the combination of a spectral and multipath component can register much larger frequency swing than the plus or minus V lambda. And coming to the last topic in the lecture, performance over a slow fading, flat fading relay channel. For this case, the discrete multipath channel with a complex envelope G of t described in equation above, a demodulated signal is described in equation 15.10, which rewrite as Z of t as a 15.34a, where R of t is equal to mod G of t. It is envelope magnitude and phi of t is its phase. Assume that channel exhibit flat fading so that multipath components are not resolvable. Then the alpha of t terms in an equation 15.34a is one of the significance interval of t need to be expressed as a resultant amplitude of alpha of t for all n phasor received in the interval. Similarly, the phase terms equations in one signaling travel need to be expressed as the resulting phase theta of t, and all n fading phases pulse that information phases received in the interval capital T. Assume also that the channel exhibit slow fading so that phase can be estimated from the received signal without significant error using PLL, that is phasor lock loop circuit. Some other approximation techniques need to be for slow and flat fading channels with the received signal statically Z of t. The demodulated signal which can be signaled in interval including the noise n out of t as Z of t is expressed in 15.34. For a simplicity, we replace alpha of t with alpha, the binding signaling over an AWGN channel with a fixed attenuation of alpha is equal to 1. The bit error rate probabilities of a basic, coherent and non-coherent PSK and orthogonal FSK is given. The plots of bit error versus EB by N0 for the signaling schemes which can manifest the classification of exponential relations. However, multipath conditions, if there is no specular signaling components, alpha is the relay distributed random variable or equivalently, and alpha scale described as a chi-square PDF under the relay fading conditions. The below figure display performance curves versus EB by N0, where E0 represent statistical expectations and the bit probability expressions for the basic binary signaling schemes shown in the figure. Each of the signaling scheme that had been manifested a waterfall shaped performance plot under AWGN interference. In this performance, taken an inverse linear function as the resultant of relay fading channel. And we have to maintain category of the modulation PSK with a probability error is 1 by 4 by EB by N0 into E of alpha square, and similarly DPSK, orthogonal frequency FSK and orthogonal frequency FSK in coherent and non-coherent values. And observe that the EB by N0 is decreases by increment of probability of error, which can be shown in the figure of 15.6. Up to this, we covered different type of a signal time spreadings, like signaling time spreading viewed in time domain, degradation categories due to the signaling time spreading viewed in time domain, signal time spreading viewed in frequency domain, and degradation categories due to the signaling time spread viewed in frequency domain, and example of flat fading with a frequency selective fading, time variations of a channel caused by the motion, and the basic fading mechanism of independent of each other, the concept of duality, degradation categories due to time variance viewed in a time domain, time variance viewed in a Doppler shift domain, and analogy of spectral broadening in fading channels, and degradation of a categories due to the time variations viewed in a Doppler shift domain, and finally performance of a slow and flat feeding in a relay channel.